Welcome to the CO2 heat pump water chiller part of this MultiPack presentation. My name is Armin Hafner. I'm from NTNU in Norway, and this presentation has been made in cooperation with Ejector and Giacomo Tosato. We will look into CO2 heat pumps and how we apply them in integrated systems. I will show you some innovative CO2 chillers, the development of them by the company NX, and how these kind of chillers are integrated into the MultiPack projects, the demo cases. And in addition, how to integrate hot water storage systems. At the end, I will give you a short summary and a conclusion for this part. What is a MultiPack reversible chiller heat pump? Well, it's an integrated unit. It can provide both heating, air conditioning, and domestic hot water. And we use carbon dioxide, the natural working fluid, as the only working fluid. We can also use air or water as a heat source and sink. We are combining ejectors and gravity evaporators to improve the performance of the CO2 chillers. And all these units are fully instrumented to measure and monitor the performance. What we want to do and what are the objectives within MultiPack, as mentioned before, is to prove the technical feasibility, the reliability, and the serviceability of these kind of units. Build them up to give confidence to the end users and to demonstrate the energy performance in the field. If you look a little bit back in history, CO2 heat pumps have been there all the way. Since about 20 years, we can find them in the market. There have been some demonstrations in the beginning in mobile air conditioning. Toyota had a fuel cell vehicle which had a heat pump functions. Around also 30 years ago, my colleague Peter Nexo, he developed the first hot water heat pump systems, and this led to an industrial implementation of this kind of technology in Japan, mainly with the EcoCute, which is producing hot water for now more than 5 million households in Japan. Why is it so good to use CO2 for this kind of systems? What are the advantages of applying CO2 as a working fluid? Well, it's a safe fluid. It's not flammable. It has no impact on the environment. We have also very high refrigerant density, which reduces the size of the compressors, especially the sweat volume, and of course it gives small refrigerant lines. Nevertheless, low pressure ratios are very beneficial when it comes, and it results in high compressor efficiency. And high heat transfer and low specific pressure drop is very beneficial in heat pump systems as refrigeration systems. What are the challenges? Well, it's the increase in heat rejection loss, which you can see here on this part of the typical TS diagram. So compared to traditional low pressure fluids, there is an increase in heat rejection loss with CO2. On the other hand, we do also have an increase in throttling loss, which is indicated by this square. So those two could be challenges, but on the other hand, when we look into some of these options, it can be an opportunity. Especially for a heat pump, the heat rejection loss is of an advantage because we can reduce the losses when we heat up a fluid from a low temperature to a very high temperature, which is the case for a hot water heat pump with CO2, because we want to heat the water at least to 70-80 degrees to avoid Legionella and all these issues. And as you can see in this graph, the area between the heat rejection curve, which is represented by the green line from 2 to 3, where heat is rejected with gliding temperatures, and red represents the water which is heated up from a low temperature to a high temperature. The area between these two is quite small. That's good, and that means a high efficiency for this process. On the other hand, remember we have these throttling losses. These losses can be turned into a possibility when we apply an ejector, which is kind of utilizing this expansion work to do something positive in the system. What is an ejector? It's a jet pump, and it has no additional work. It is a free pressure lift which can be implemented. It has no moving part, it's easy to install and operate and maintain. And it works after the Bernoulli principle. When the speed of a fluid increases, its pressure decreases, and vice versa. So high pressure fluid enters the nozzle in A, where pressure energy is converted to kinetic energy. We get very, very high velocity at the outlet of the nozzle. The fluid at low pressure, which comes typically from an evaporator, is sucked into the nozzle, and the two streams are mixed in the mixing section, and the pressure is increased further in the diffuser as the velocity of the stream decreases. So then we can see that we have an outlet pressure which is far higher than the suction pressure which comes in from the nozzle B. What are innovative chiller developments performed by NX? Well, 5 years ago, 2015, the first gravity feeding chiller was developed and put into the market. It has a low delta T at part load, and it has a dynamic set point. It's very robust and reliable. 2 years later, it was introduced the gravity evaporator, which is still here in place. And in addition, so this is the gravity evaporator, fed only by gravity. In addition, there has been an ejector supported evaporator, where the ejector is sucking all the vapor which is evaporated in the second evaporator. Means we have a plus 5 to 15% efficiency gain in this, and we can have a higher temperature difference on the water side. Simple control, self-adjusting, and there is no climate restrictions for these kind of systems anymore. In the beginning of the MultiPack project, before the MultiPack project, these kind of systems were integrated, where a chiller and the heat recovery unit has been kind of combined. Hot water, domestic hot water can be made, can be also used for space heating. The gravity and/or ejector supported evaporator is integrated, and there is a high pressure optimization for the whole system. Within the MultiPack project, you can see now the sketch of the outline of how the heat pump water chiller looks like. The main features are, it's all in one unit. It's a chilled water unit. It can produce domestic hot water. It has a heat exchanger, a kind of place where we can support space heating demands. It's air to water heat pump with a hot gas defrost. So the external heat exchanger is utilized as the evaporator or a heat rejection device. It uses the non-flammable refrigerant CO2, which is an A1 fluid. It's safe, and it has no location restrictions when it comes to performance. It's simple and inexpensive installation. I will now explain further the different modes of this unit. For example, if we have the chiller mode, where we produce cold water, chilled water, and reject all the heat towards the ambient air. Then you can see the compressors are operating. The gas is directly guided towards the external heat exchanger, which is in this case operating as a gas cooler. High side pressure is then further cooled down by a suction line heat exchanger, providing superheat for the compressors, where then afterwards the high side pressure is expanded into a separating tank. And mainly this is done by the ejectors, because then this expansion work can be utilized to maintain, to operate the low temperature evaporator, which is, as I said, supported by the ejector. While the first evaporator, where the water is chilled in the first place, is a gravity-fed evaporator only. So the second stage of the cooling of the chilled water takes place in the evaporator, which is supported by the ejector, which has a somehow lower pressure level then the first evaporator. So it's a pre-chilling and an after-chilling of the water. So this is how this mode is operated. There is another operation mode, for example, a heat pump mode, where air is utilized and water is produced. In this case, the ambient air is the heat source. It's a heat pump, space heating. It's a classic low pressure receiver system where you can see the compressor, the gas from the compressor is guided towards the heat exchanger, which rejects the heat towards the space heating. So this space heating water loop is heated up. CO2 is further cooled in the internal heat exchanger before expansion takes place towards the exterior heat exchanger, which is operated as an evaporator before the two-phase or nearly two-phase flow is going into the low pressure receiver, where the CO2 is stored in case the high side pressure has to be adjusted. So, and then the gas is sucked by the compressor back. So this is how it works. In this case, we can utilize simultaneous production of domestic hot water and additional space heating. In this case, I just show you the space heating, but of course, we could have guided the hot CO2 first to the domestic hot water and later on to the space heating, even more utilizing the gliding heat rejection at constant pressure. Another way to utilize the heat pump water chiller in these demo sites is to use chiller function and domestic hot water. And if necessary, some of the heat can even be rejected. If it depends a lot on the hot water temperature and the return temperature of that water. So, as I said, in this case, CO2 comes from the compressors, goes to the domestic hot water heat exchanger. Hot water is produced. Depending on the temperature, the gas can either be sent directly to the expansion device, to the ejector mainly, or it goes to a further heat rejection if there is much more load on the chiller part than it is on the hot water demand, depending on the functions. So we produce hot water, we reject some of the heat towards the ambient, and heat is taken from the chilled water loop to provide cooling. It's partly heat rejection to ambient, depending, as I said, on the cold water inlet temperature. Yes. And we can also, of course, in this case, utilize the space heating heat exchanger to, in addition, provide heat for space heating, if necessary. This is a picture of the unit, how it is installed in the workshop during the commissioning phase of the MultiPack project. So we can do, with this fully instrumented unit, a lot of tests, bench tests, so it is easier to implement and validate these kind of results in the tools which are developed and to disseminate results. In that case, we have control boundaries, which is not always the case in the demo sites. We are not able to control the air side because the exterior heat exchanger is placed outside and the climate changes from day to day, but we have to select certain test periods with certain ambient temperatures to compare. This is an example on two tests. One test is done with a high load and the second test is done on a low load. What means high load? High load means in this case two compressors are on and with the inverter 50 Hz. The high side pressure is adjusted to 99 bar. The temperature out of the gas cooler is 38.5 degrees C. The achieved COP was 4.9 and the electric power supplied to the unit was 49 kilowatt. How was the performance of the important parts, which are the chiller unit, the chiller part, how much water could be cooled and how much hot water can be produced? And I show you here the results. The water came in with 14.1 degrees C. In the first heat exchanger, which is gravity fed, it was cooled down to 11.1 degree, and then towards the second heat exchanger, which is supported by the ejector, it came down to 6.8 degrees C. That means the total cooling capacity is it's a bit higher than 100 kilowatt. The first heat exchanger removed about 43 kilowatt, while the second removed 61 kilowatt. On the other side, we produced hot water. The water came in with a relatively high temperature of 30 degrees, and it was discharged with 60 degrees, and the flow rate corresponded to a capacity of about 132 kilowatt. So this was the high load operation. And on the low load operation, we just applied one compressor. The high pressure was a little bit lower. It was adjusted to 94 bar. The outlet of the gas cooler was a little bit lower, 36.5, and the COP was a bit higher, which was achieved. The power was only about half, 23 kilowatt. The water was in this case cooled down from 11 to 7 degrees. In the first place, half of the capacity was in each of the evaporators, down to 9 degrees after the first evaporator, which took out 30 kilowatt, and the second one another 30 kilowatt. So in total 60 kilowatt of cooling capacity. On the other hand, water again was heated up from 30 to 60 degrees, and it corresponded to about 67 kilowatt. So these two cases show it is possible to achieve a relatively high COPs and to have these functions in one unit. When we look at the high load test and look at the performance inside these two, on the cold side, you can see the water profile. It's about 14 degrees down to 7, where we have an evaporating pressure level of about 8 degrees in the first evaporator, and the second one, which is supported by the ejector, has a evaporating of around somewhere around 3 degrees C. By doing so, we can achieve this high temperature glide on the water side, and the estimated energy saving compared to have a single evaporating temperature is about 10%. So it means we can have a great benefit if we have a large water delta T temperature difference, which is the case especially in processed chillers. On the low load, you can see we have a less capacity on the ejectors because of the mass flow rate is more or less reduced to half. However, still we have a different pressure level in the two evaporators, and it can be demonstrated how this works, and the saving is still around 7%. If we compare only to the gravity evaporator, that's why we can achieve more if we implement the ejector in addition. When it comes to the capacities, it's just to illustrate where has been the high side pressure adjusted between 94 and 99 bar. We had a cooling of the water from 11 to 7 degrees mainly, and the different the share of the cooling can be demonstrated here, where you can see that in case we have a lower capacity on the heating side, as indicated by the red bars, we can see the higher the ambient, or the higher the high side pressure and the capacity, and the outlet temperature of the gas cooler. Yes. So then the share of the flooded evaporator goes down, because the higher the potential of the work recovery, the more capacity can be done by the ejector supported evaporator, which is represented by the light blue bar, while the dark blue is the flooded evaporator. Yes. And then I would like to highlight how we should integrate the hot water storage system. So on the left hand side you see a simple version of the heat pump. It could be also the MultiPack integrated heat pump water chiller, but we are just focusing now what what can be done with this hot water and how should it be treated that it is always the coldest water which comes back towards the heat pump, because the heat pump is very efficient if the return temperature is low. I just illustrate this with 4 storage tanks which could be adjusted or implemented in a high performance building like a hotel or a place where you have a lot of hot water demand. This case shows that most of the storage tanks are empty, indicated by the blue color. On the right hand side you can see a circulation system. So the yellow line indicates that the water is circulated towards the building, supported by a pump. So the return temperature will be lower because we are circulating between 65 and 75 degree water towards the different users. And of course there will be a return, and due to heat loss this will be lower. So what we will do with this heat pump, we will also reheat the circulated water with energy coming from the heat pump. This is done by supplying the water with 85 degrees out of the heat pump towards the storage system. Then it goes into a heat exchanger, a coil heat exchanger, which is integrated in this small tank, which is reheating the water which is circulated and slightly cooling down the water before it goes to the storage with approximately 75 degrees C. So whenever you see the red line, the red color inside the storage tank, it represents about 75 degrees. When this is the case when the heat pump is starts to charge. This is the case when the heat pump has fully charged the storage and the return temperature starts to increase about a certain level. Then the heat pump stops, is turned off. The circulation pump here stops again, and the system is ready to be supply the water towards the building. If nobody takes out water from the circuit, then also no cold water is coming in, but circulation still takes place. The heat loss is still going on here. We have to support the reheating of this water. It could be done by a backup reheater with electricity, but that is not very energy efficient. So in this case, we propose to install a reheat function with circulated water utilizing the stored energy in the tanks. So this controller checks that the temperature of the water which is pushed back into the tank is at least 65 degrees C. So approximately 10 Kelvin or more temperature difference can be utilized to reheat the water which is circulated with the energy stored in the tanks. So, and after a while the consumption is back to normal. After the night is over or consumption comes back, then the heat pump switches on anyhow and we are back to normal reheating based on the heat pump. So this function is only activated when the heat pump stops because the tanks are fully charged. On the other side, the last tank or the tank where the cold water comes in normally may have a challenge to reach these high temperatures, because it's necessary to have a high temperature in the tank to kill the Legionella bacteria from time to time. That's why every 14 days in this heat pump off session, when the tanks are fully charged, there kicks in a pump which is circulating the water only through the last tank, and it is reheated to 75 degrees for a short period to make sure that it has reached this high temperature. So by doing so, by designing the hot storage water system in this way, we can assure that we have a very high efficiency also on the water storage system, which is essential to have a high COP of the entire heat pump system. This brings me now to the summary. It has been shown in this part of the presentation from MultiPack that CO2 chillers are available and are a safe option for the global market. So the design of these units is completely defined. There is no new things which have to be added. They are completely defined. The control logic has been optimized with an extensive test program and campaign. The tests are performed and the feedbacks of the control they are continuing. And we have field data from chillers and chiller and domestic hot water operations. They will be presented on our websites and in other dissemination events. A transient numerical model is also made and is validated with these kind of experiments we get from these sites. And it will be used to further tune the logic of the control, and last but not least, also to give a prediction of the performance at variable boundary conditions for other projects. So that's why it is utilized. The conclusion is that a smart integration of ejector technology improved the energy efficiency of CO2 units, especially the chillers, and especially also where we have a high temperature glide, also on the cold water side for process chillers and so on. Safety and service of service people is very, very important and has a very high priority for the end users. That's why we believe this total environmental impact, which can be shown by a CO2 system, has a significant influence. And the CO2 systems are successfully introduced in some markets already. Last but not least, training is very, very important, and the knowledge how to use this system, how to do it, how to perform integration, commissioning, servicing is very important. I believe that the World Bank and the multilateral funds should support and cover additional costs with affordable loans, so end users are not kind of afraid to have a little bit higher investment. However, they save a lot of energy when utilizing this kind of system, which helps them to reduce the OPEX. And with that saving, they can pay back easily these loans. Thank you very much for your attention for this part. If you have any question, please contact me or my colleague Engin. We will help you to answer the question and find solutions for you as well. And once again, thanks for you to supporting us, and hope to see you again. Thanks.